Hello and welcome to the first Slick Screencast. Today I'd like to give you an overview of the query compiler. And for that purpose, we're looking at the topic/codegen phase branch. This code is not yet in master, but it should be there soon. Here we have the main class, which is simply called query compiler. Just like the trees and types, the query compiler is almost entirely immutable. You can see several methods here, which add or remove phases, and they all construct a new query compiler. The query compiler consists of a number of phases, and down here we have the list of the standard phases, which should be run for any kind of backend. And here are phases which are concerned with converting the tree that comes out of the standard phases into something suitable for SQL code generation. Down here we see the phase class, which describes a single phase. It has a state that the phase can set, and that other phases can later query to find some accessory information left by that phase. Each phase has a name, which is the same as the variable names we see down here or up there in the list. And here's the apply method for the phase, which is simply a transformation from a compiler state to a new compiler state. The compiler state is defined down here. You can see that it consists of the compiler, the current tree, and the state left by the previous phases. There's also a symbol namer, which is responsible for giving names to symbols. In order to see the compiler in action, we'll need some test code. So we're going to new query semantics test. There's a method called test new composition, and we're just running the first query defined here, that's QA, which is a rather simple query. So let's just comment out everything in that method after QA down to the end of the method, which should be here. And now we're going to run it in SBT. So I'm using test only -- so that all remaining arguments are passed on to JUnit interface, which knows how to filter on the individual test methods. And we're testing new composition, and we're only running it against the H2 in-memory database. Okay, the test was successful, but we didn't get any output. For that, we first need to enable standard out, which is usually suppressed for successful test cases, and we also need to turn on logging. Here you can see the logback configuration used by Slick's test kit. All the logging in Slick happens at the debug level, and the default we're setting here is info, and all the other loggers inherit from it. What we need to enable is the logging for the query compiler. That's where the output of each phase is logged. So we need to set the system property log.qcomp.phases to debug. Let's try that. -d log.qcomp.phases equals debug, and run the tests again. And now we're getting some output, quite a lot actually. So here at the top, this line is printed by the actual test case, and down here is the first log statement. That's the source of the query AST. Each line in there represents one node in the AST. For example, the top level node here is called bind. The children of each node have names. In bind we have a from node with a symbol name attached to it, and we have a select node. The from node is a ref node, the select node is a pure node, and pure again has a child called value, which is a product node, and so on. The ref we see up here refers to an intrinsic symbol. It's represented by its identity hash code. Each node in the tree has one intrinsic symbol associated with it, and you can navigate from the node to the symbol and back. The advantage of this system is that we do not need any global symbol cache when we're constructing the AST. This source AST is not actually a tree but a forest. In addition to this bind node at the top level, we also see a second node at the same level, and that was discovered from the intrinsic symbol here. So we just followed the symbol and discovered the node, and we print it. The downside of these intrinsic symbols is that we cannot do any useful transformation of the tree. For example, if we wanted to replace this take node by some other node, we couldn't easily do it because there's an intrinsic symbol that points to it, and this symbol, which is referenced up here, can never point to any other node. So the first thing we need to do in the first compiler phase, which is localize refs, is to replace these intrinsic symbols with anon symbols. If we look at the output of localized refs, we can see that it's almost the same as the source tree. The bind node at the top level now appears in this position, and its children are almost the same, except for one difference. The ref to the intrinsic symbol here is now a ref to an anon symbol, and the definition is found up here. That's the same one we've seen in the source. At the top level we have a new let dynamic node, which ensures that we now have a proper tree instead of a forest. All the referenced symbols, which used to be intrinsic symbols, now appear as let clauses of this let dynamic. It doesn't matter in which order they appear if we have several of them, because the dynamic here refers to the dynamic scope. This will be resolved in a later compiler phase. Let's look at the implementation of the localize refs phase. The main feature we see here is a transformer, which is a utility class that allows you to transform a tree recursively. You can run it in different modes, like transforming it only once or transforming it until there are no more changes to be performed. In this case, we're running it only once against the original tree. The transformer has a replace method, which is a partial function that pattern matches on things to replace and returns the replacement for them. So here we're pattern matching on a ref node, which is an abstraction for all nodes that have a reference to some symbol. We've already seen the ref node implementation, but there are a few others, and there's a common extractor for that, so we can catch everything with a single pattern match. And what we do here is that we create a new anon symbol, and we add it to this maps so that it points to the target, and then we are returning a copy of the original ref node R with the new reference that we created, the new anon symbol, and we're also copying the original type in case this node already had a type associated with it. Now we're running this transformation once on the whole tree, and then we're collecting the new nodes that we discovered. And we're repeating this process until there are no more nodes to discover. And in the end, if we didn't get any additional nodes, we just return this transformed tree. So we don't need a let dynamic because there are no symbols to bind. If we discovered any symbols that we replaced, then we create this top level let dynamic node. Well, that's it for today. Next time we're going to take a closer look at the node implementation and the next compiler phase.